Today's video lesson is on chords and arcs. Objectives: to use congruent chords, arcs, and central angles, and to use perpendicular bisectors to chords. You can use information about congruent parts of a circle or congruent circles to find information about other parts of the circle or circles. So the diagram below shows chord PQ, and it relates to arc PQ. So for every chord, it creates an arc. So for chord PQ also will create arc PQ, and remember that it's two letters, therefore PQ is a minor arc. So a chord is a segment whose endpoints are on a circle, so PQ is a chord. OA is not a chord, it's a radius, because both endpoints are not on the circle. Just because one endpoint A is on the circle, endpoint O is not on the circle, therefore O to A is not a chord. So this is not a chord. PQ is a chord. So again, a chord is a segment whose endpoints are on a circle. So we have our first theorem, which states that if our central angles are congruent, then our arcs are also congruent. So if I know that angle O, the central angles, okay, AOB and COD, if they're congruent, I know that the arcs are also congruent. And vice versa. If I know the arc AB is equal to arc CD, then I know that the central angles will also be congruent that corresponds to those arcs. So an example to this would be if I have two circles, or not even two circles. If I quickly draw a circle with two central angles. So I have A, B, C, D, and E. If I know this is 50, 50, and this is 50, therefore since my central angles are equal, I know that the arcs DE and AB are equal 50. And remember that these AB, these are arc lengths. Okay? It's also referring to the arc measures. So if the arc lengths are equal, the central angles are equal, or vice versa. So let's summarize here. So I have two central angles, so these are the central angles. These are arc lengths. So if central angles equal or congruent, then the arc lengths are congruent. Or you can have, if your arc lengths are congruent, then your central angles are congruent. You have a second theorem, which states if your central angles are congruent, then the chords constructed by the central angles are congruent. So if I know angle O here and this part of angle O, so BOA and COD are equal, then I know these chords AB and CD are congruent. So a short example, or a mini example, so if I have two central angles, I have chords formed by the central angle. So if I know that this angle and this angle are congruent, then I know that this chord and this chord are congruent. And vice versa. If I know that those two chords are equal, then I know that these two angles are equal, the central angles. Next, if I have two chords equal, congruent, that means then the intercepted arcs formed by the chords are also congruent. Okay. So example, circle. If I have two chords, okay, if I know that these two chords are equal, then the arcs formed by those two chords, or I should say the arcs intercepted by those two chords, are congruent. So I know that this arc AB is going to be the same as arc CD. So again, that was if I know that those two chords AB and CD are congruent, then the arcs intercepted by those chords are congruent. So arc AB is congruent to arc CD. and it's vice versa. If I know that the arcs AB is congruent to arc CD, then the chords will be congruent. So AB is congruent to CD. So we can use those theorems to conclude information from two congruent circles. So if I know these two congruent circles, the only thing I know that the radii will be congruent. That's all I can conclude if I know I have congruent circles. So BC and DF, those are chords. So I know that if these chords are congruent, I know arc BC is congruent to arc DF, and I know that angle O is going to be congruent to angle P. Why? Because I had chords BC congruent to chord DF. So that's using the theorems that we just went over. So if your chords are equal, your central angles are equal. If your chords are equal, the arc are equal. And you can rearrange any of those methods as you wish. Meaning that if you know the angles are equal, the chords are equal. If the angles are equal, the arcs are equal. If the arcs are equal, the angles are equal. So there's a lot of different combinations you can do. Here's a good problem reasoning. We're going to use the same pictures from the previous slide, and we know that the circles are congruent. So if I know my circles are congruent, I know that the radii are congruent. And I know that angle OBC is congruent to angle PDF. Okay, well, I know that if these two circles are congruent, I know that OB, OC, PD, PF, those are all congruent. So BO is congruent to CO, which is congruent to DP, which is congruent to FP. So all those radii are equal. Okay. Okay. Why are those? Because radii are congruent in congruent circles. Well, to prove that angles O and P are the same, well, now I have isosceles triangles. So if I have isosceles triangles, I know that angle C and angle F are congruent. So I know that angle B is congruent to angle C. I know angle D is congruent to angle F. And I know that angles B, C, D, and F all congruent, okay, because we have base angles congruent in isosceles triangles, and we have congruent circles. Therefore, I know now that angle O and angle P, angle O and angle P are congruent because of the third angle rule. So if I know that I have two congruent triangles, I have two congruent pairs of angles in two different triangles, it makes the third angles congruent. You could also say, okay, or that because of angle side, okay, I have congruent triangles by angle side, therefore I have corresponding parts of congruent triangles are congruent. Here's another theorem dealing with chords and circles. So if I have OE and OF congruent, then I know the chords AB and CD are congruent. Also, I know that they will be bisectors, so I know that those two, all of these segments are going to be congruent. And this will only happen if parts of the radii, OE and OF, are perpendicular to the chord. So again, key here is you have to see perpendicular, okay? and then you know that parts of the chord, or sorry, parts of the radii O, E, O, F are also bisectors as long as it's perpendicular to the chord. So example here. I have O, Q, O, we'll do Z, they're congruent. So if I know that parts of the radii are congruent and perpendicular to a chord, I know that the chords will be equal and the parts of the radii will also be bisectors. So I know that this is 12.5. And then the whole thing here is 25, therefore SR is also 25. What's the value of X? I know X is 16. Okay, I know X is 16 right off the bat because I see that I'm perpendicular. So if I'm perpendicular, I need to be a bisector, and I need to be congruent to the other chord. Okay, so I know X is 16. Okay, here's how I know X is 16. This is how I would explain it in a quiz or test. So I'll label A, B, C, D, E, F. So I know X is 16. Why? Because AB is bisected and congruent to EF. And I know that AB is perpendicular to CD and EF is perpendicular to D. I'll say this is Q. So that's my reasoning of why X is 16, because I know AB is bisected and it's also congruent to EF, and I also know that AB is perpendicular to CD, and I know that EF is also perpendicular to DQ. You also have 3 rules that deal with the diameter in a chord. So if a diameter and a chord intersect at 90 degrees, therefore the chord will be bisected. If a chord is being bisected by a diameter, that makes the intersection of a chord and diameter perpendicular. And the last rule is if you have 2 lines or 2 chords that are perpendicular, one of them being a bisector, then the bisector is going to contain the center of the circle. So we can apply these rules. So I have K to N is perpendicular. Okay, if it's perpendicular, you should also notice the shortest distance from a point to a line or point to a segment is a perpendicular segment. So since KN is perpendicular, I know that LN and NM are going to be bisected. Or sorry, LN is congruent to NM. Therefore, LM is being bisected. So I have a right triangle. So this is 3, this is 7, this is R, 90 degrees. Pythagorean theorem. So I have 3 squared plus 7 squared equals R squared. So 9 plus 49 equals R squared. I have 58 equals R squared. The square root of 58 equals R. I want to round to the nearest tenth. So if I do the square root of 58 and round to the nearest tenth, it's 7.6. So R is about 7.6 centimeters. That's the radius. What's the value of each variable to the nearest tenth? So there's only one variable, and it is y. Well, since I have part of CB is bisecting AF, I know that angle C is 90 degrees. And since 15 is representing a radius, don't forget you can move a radius in any circle. So just because B to E is the radius, okay, doesn't mean that B to E has to be fixed at this point. I'm going to move my radius, so if B to E is here, I'm going to move my radius from B to A. I can do that. And if you move a radius in a circle, the radius will never change length as long as the circle stays the same. So since my circle stayed the same, I just moved my radius. Instead of BE, it's now BA. Well, my radius is 15, so my radius is still 15. Then you have a right triangle. So I have y, I have 15, and 11. So now it's Pythagorean theorem because it's a right triangle with two given sides and a missing side. So I have 11 squared plus y squared equals 15 squared. I have 121 plus y squared equals 225. Y squared equals 104. Y equals the square root of 104 to the nearest tenth. So square root 104 to the nearest tenth is 10.2. units. And that is 10.2. Now remember, y is not the entire radius, it's part of a radius. And that concludes this lesson about chords and arcs. If you have any questions, leave a comment or email me.